I want to welcome you to the Science Education, a local and national perspective talk tonight and panel discussion. I am Erin Dragato, Managing Director of the Chicago Council on Science and Technology, which is working to raise the awareness of science and technology issues that are apparent in our region. And we do that by partnering with putting on a regular series of programs and partnering so far with over 40 organizations, one of which being the Center for Human Potential and Public Policy for the second time. So we're really excited to be partnering with them again. And we're able to do this through our funders, and obviously, and most important, is our members. So please, if you are interested in our organization on a programmatic level, we have information out on the tables about how to sign up for membership as well. But we do produce programs on a monthly basis, and very exciting, by the way. One thing I was told to mention is there's a meetup group happening after this talk at Elephant Castle down the street, and it's just another way to continue the conversation. So look for Justin, who's over, if you want to head down with everybody to continue the conversation. And with that, I will introduce Laurel Spindell, the Associate Director for the Center on Human Potential and Public Policy at the Harris School of Public Policy, University of Chicago.
Thanks, Erin. I know our title is a little bit of a mouthful. We're really pleased to be doing this for the second year with the Chicago Council on Science and Technology. This is the Center for Human Potential and Public Policy's third annual lecture on science, technology, and society. The Center for Human Potential examines achievement, health, and well-being over the life course. Tonight we have the opportunity to examine some of the biggest challenges that science education is facing. Given the current administration's focus on improving education, especially in the area of science education, we're fortunate to have some of the foremost experts from the research, policy, and foundation communities to guide us through this issue from a local and national perspective. We're especially delighted to have Dr. Heidi Schweingruber begin our evening with a lecture on what research can tell us about improving K-12 science education. The lecture will be followed by a panel discussion during which Professor Jeanne, Mr. Michael Lach, and Ms. Gudelia Lopez will have the opportunity to respond to Dr. Schweingruber's remarks and provide some discussion-generating comments. Professor Ofer Malamud from the Harris School of Public Policy will be moderating this panel discussion, as well as the audience Q&A to follow. Last but certainly not least, as Rapporteur, Professor Jim Spillane will take on the challenge of summarizing and integrating all that has been said this evening and provide us with some thought-provoking questions to consider, which we'll be able to debate on an online forum on the C2S website. And I will send you all an email tomorrow with what that website address is. In the interest of time, I'm just going to introduce Dr. Schweingruber, our keynote speaker. Please refer to your programs for detailed bios on the other speakers. Heidi Schweingruber is the Deputy Director of the Board on Science Education at the National Research Council. Dr. Schweingruber has played a lead role in all of the major projects of the board since it was formed in 2004, and she has a long history of engaging in cutting-edge research on science education, not only in positions in government, but also in the academy. Dr. Schweingruber's background puts her in a unique position to provide us with an informed perspective on an issue that cuts across areas as significant as global competitiveness, equality, and citizenship. I'd like to thank all the participants as well as each of you for coming to this event. If I can please ask you to silence your cell phones, we'll get started with what should be a stimulating and informative evening. Thank you.
It's really a pleasure to be here. I actually grew up in the Chicago area, so this is really coming home for me. I wish I'd brought a little better weather for all of you. I understand I ushered out some really nice days. Hopefully this will clear up soon. I'm going to give kind of a whirlwind tour of science education from a national perspective. Part of my intent is really to put a number of issues on the table and provide a lot of fodder for good questions, comments, and discussion. So I want to start by giving you a better sense of what the Board on Science Education is and where we are at the NRC. The National Research Council is part of the National Academies and associated with the National Academy of Sciences, which is an honorary society of scientists. And we really exist to give evidence-based advice to the government on issues related to science and technology. It was actually established by Abraham Lincoln over 100 years ago. We're a non-governmental agency, a private nonprofit, so a very unique standing related to the government. And the board was founded in 2004 to do work in science education and especially to inject an understanding of evidence into policy discussions about science education. So we really exist at the intersection of research and policy. So before I dig into the details about the system and what the current situation is in science education, I wanted to give a brief touch on why should we care about science education. And science education, sometimes STEM more broadly, science, technology, engineering, and math education has really come to the forefront of the federal landscape over the last few years. And the typical arguments advanced for the increased attention often revolve around global competitiveness and the workforce. So the idea is in a flat world, we need to be competitive internationally, and the way you're going to be competitive is to have a strong science and technical workforce that can drive innovation. In addition, a lot of jobs across the economy require more science and technical skills. More recent reports, and I would concur, raise some other what I consider to be more important issues, which are things like public participation in debates about issues like global warming, environmental issues, health issues, and it's taking an increasingly deep knowledge of science to really be able to participate in discussion of those issues. Like health, even what car or furnace you'd want to buy really require a better foundation in science education if we want to make good choices. And finally, equity. And I'm going to touch on this equity theme across the talk. There's really a lot of evidence that while we might have some problems in science education, we particularly have a problem with equity and really reaching diverse populations of kids. So what is all the alarm about? I want to lay some groundwork here and give you a sense, just a quick snapshot of what we know about how kids are doing in science K-12. These are scores from the National Assessment of Educational Progress, which is administered by the National Center for Education Statistics in the Department of Education at the national level. There's several forms of the test. The form that you see here are scores from a longitudinal test that can be tracked over time. These are scores from 1996 to 2005. Those are the latest scores available. There's another round in 2009, but those scores won't be out till the spring of 2010. What you see is flat performance in 4th, 8th, and 12th grade, which might not be alarming except that these are relatively low scores. And at the 12th grade, you can actually see there's a significant drop. Not huge, but a drop from 96. A lot of the alarm bells are actually raised because overall in international comparisons of performance, American students tend to perform at much lower levels than other students in other developed countries. So the countries that we would consider to be our economic peers, typically our students are not doing as well as students in those countries. My first sort of indicator of this problem with equity, when you disaggregate those overall trends by different groups of students, you see an alarming gap that's not closing. So across lots of subject areas since the 1970s, we have seen gaps close, and that's been the same in science and math. But over the last 10 years or so, we haven't seen the gaps closing. So you can see the yellow box at the top are white students. The Asian students are then the red circle, and clustered a significant amount below those are American Indian and Native Alaskan, Hispanic, and Black students. And this is sort of a chronic disparity that we really need to figure out what to do about it. So that gives you a quick snapshot of why we care about science education and sort of the state of student performance. What I want to do now is dig into what's leading to those problems with performance, what's leading to the alarm about science education in general, and people being concerned that we have to do something to fix the system. So at the very broad level, I want to first tell you a little bit about the federal context. So in education, in science education specifically, at the federal level, science education really lives in more than one agency. So there's not one federal agency that has responsibility for education. And I've actually listed, for science education, I've actually listed the 6 agencies that do have programs related to K-12 education. Most of the funding actually for K-12 comes from the National Science Foundation and the Department of Education. I should point out that in the Department of Education, at least in the time that I've been in DC, which is since 2000, there hasn't been a go-to person for science education. So when we want to contact the department, we don't actually know who to talk to because there isn't necessarily someone who does science education. There's also funding in NASA, NOAA, the Department of Energy that goes to different programs in K-12, but there's overall kind of a lack of coordination about what's going on at the federal level. In fact, in education generally, the action really isn't as much at the federal level as it is at the state and local level. And this is a matter of political will, a sense that across the history of the U.S., education has really been seen as a local and regional issue. You want people to be able to educate their kids and focus on the topics that matter to them. And so there's really a tension in political discussions about how much can actually be done federally. And that's the same is true for science education. So what's going on in the system out there across the 50 states? When we talk about science education and the system for science education, we're actually talking about a very complex beast. There are many different elements that have to work together to support what's going on in the classroom. And I've kind of represented this here with several key elements. And to me, the intersection of those is the classroom. And we want to look at the classroom because that's where learning happens. That's where whatever those students are experiencing is producing that achievement that I talked about. So we've got to understand what's going on in the classroom. But to understand what's going on in the classroom, you also have to know how that's shaped and constrained by what's going on with these elements of the system. So I'm going to talk obviously briefly about 4 of these today: the assessment, standards, curriculum, and the teaching workforce. I'm not going to get into school organization and administration, but as you may imagine, that's also very critical to understand. So first touching on standards. There's been a standards movement in education for, say, the last 15 to 20 years. And standards are the sets of expectations for what kids should do over multiple grades in a particular subject. These are, again, not federal in the sense that there's no government agency that creates them and lays them out. In fact, the Department of Education is not allowed to do that. Unlike some other countries where it is a government function, here, when we have standards, they've typically been a professional organization or something like that that creates them and puts them out there for people to use voluntarily. Interestingly, in science, we actually have 2 sets of national standards of those sort. One comes from my organization. They're called the National Science Education Standards. One comes out of the the American Association for the Advancement of Science, AAAS, and those are called the Science Benchmarks. Then what happens is those 2 sets of standards exist. States in developing their own standards will look at them and then translate them into guidelines at the state level. We know that there's some variation depending on which of those 2 national documents states have decided to use as their source document. We also know from analysis across the states that there's huge variation in what actually ends up in those state standards. And in fact, huge variation between what's theoretically the source document and then what the states actually do. So we end up with this incredibly diverse set of targets for science education across the grades. In addition, a general criticism in science, but also in mathematics, is that standards in curricula are what's been called a mile wide and an inch deep. So we have a huge number of topics in a lot of these standards, very disconnected and given equal priority. So there's not direction given to whether this particular topic actually is more important as an explanatory idea in science than another one. So we tend to get this drive for coverage. So this sort of sense of, oh my gosh, we only have this many months in the school year. I got to get through this whole set of standards for this grade, so I'm just going to push for coverage. I'm going to do this really fast. Instead of allowing time for really sticking with a topic, delving into it in depth, and really pushing for mastery and learning. In addition, the variation in standards that I described across states creates a really complex landscape for people developing textbooks and curricula. So you can think of those 50 states as a market. If you've got a huge variation across the states in what they're aiming for as targets, how do you market to all that variation? And what often happens is you, again, get a textbook jammed full of topics, but they're not necessarily thoughtfully sequenced, and they end up with what I've called here modularity. So the idea that in order to let states and schools and districts and even teachers tailor it to their local needs, we're just going to let them pick and choose and kind of move things around and use what they need to. So again, you get this lack of coherence in the system. Now, assessment is another piece, another element of the system. It's become, large-scale assessment particularly has become more and more important given the increased emphasis on accountability, and that really has come out of No Child Left Behind specifically, but No Child Left Behind came out of already established momentum toward wanting to have some system of accountability for schools. So it's not just the fault of No Child Left Behind. There was already momentum there. Now, science originally was not tested under No Child Left Behind, but then it came online. But it isn't part of what's called adequate yearly progress, and this is kind of the stick, that if you don't meet adequate yearly progress, that's when you start to get in trouble as a school. Math and reading are part of that. Science is not. So science is tested, but there's no real stick related to science. Now, I'm not suggesting you want the stick in science, because there's a lot of debate about whether that would be good or bad, but I'm just saying that is the current situation. One of the problems with science coming online as being tested under this system is that it requires large-scale tests that can be taken by lots of kids, and really you kind of got to do that cheaply. Well, the technology for doing that in science is not particularly good. What you often end up with are sort of poorly developed, poorly designed multiple choice tests that touch on terms, facts, don't really dig into science in a deeper way, and very much don't touch on what's typically called science process. And I'll describe this a little bit more. The kinds of reasoning and investigations and interpretation of data that are really a fundamental part of science. So next I'm going to look at the teaching workforce. Okay, and in a lot of the reports that have been released nationally, which are calling attention to this problem in science education, the teaching workforce and teacher qualifications are really what's pointed to as sort of a linchpin things that need to change. And that is true, but it's not necessarily a simple fix of just pumping in people who know a lot of science. So let me lay out the challenges, and they do differ by level of schooling. So in addition to this complexity of standards, assessment, whatever, we also have different levels of schooling that are structured in different ways. Elementary, middle school, and junior high and high school are structured very differently. And science has a very different place in those different levels. So at the elementary level, K-5, you have one teacher teaching all of the subjects typically, and science will be one of those subjects. In middle school and high school, you're starting to get differentiation into different courses. At high school, you clearly need a credential that's somehow related to science to be able to teach that class. In middle school, we have a much more complicated setting because some people can get a K-8 credential and don't necessarily need to have a specific foundation in science with that K-8 credential. So one of the problems that we want to look at is whether the teacher who's in the classroom in front of the kids really has a grounding in science, because there's general agreement that in order to be able to teach well, you need to know something about the subject. I think that's kind of a no-brainer. That you need to know about what you're teaching in order to be able to teach it well. So one of the ways that people have looked at this is called out-of-field teaching. Now, there are different ways to measure out-of-field teaching. Sometimes it's measured by looking at people's major teaching assignments. So that might mean I typically teach biology. There's some evidence that that's actually going to undercount how many students experience a teacher in a classroom who's teaching out of field. And that's because someone might have a major assignment, but then they also may pick up a couple courses and cover them. And so the statistics I'm showing you here are actually students who have experienced a teacher who's teaching out of field. Okay? I think these are more accurate when we're trying to get at what's happening in the learning experiences for students. So what I'm showing you here is in the dark blue. This is really a high bar for teacher qualification. This combines two things that people have identified as being really a marker of a high-quality teacher. So it's having both the major and certification. So what you're seeing in the blue bar is the percentage of teachers who don't have those two things, okay? It's maybe a little alarming, although you might say at middle school, you're not going to be delving into topics in science that are terribly sophisticated, so it might not be alarming that over 90% of your middle school physical science teachers are one of those people who don't have major or certification. The light blue bar, I think, is more problematic, and that is basically no credential in the science that you're teaching. No major, minor, or certification. So no documentation that you really know this field. If you look at the middle school here, again, 40% of kids are experiencing teacher who doesn't have some kind of documentation that they have a background in that science. That's problematic. Further problematic is when you break this down by minority enrollment, and in a second I'll show you schools with high poverty, concentrations of kids in poverty. These are schools, what you see is the percentage of minority students, and you can see high school's not as much of a problem, but the middle school, we really have an issue where some of these kids, who in fact may need more support instructionally, depending on the other things that are happening in their lives, they're actually getting the teachers more often who don't have the background in science. And so this is where we see that sort of problem of equity coming up again. And similarly, you see a similar trend for students with high concentrations of low-income students. So what does this all mean? Now I want to draw down into the classroom. So this is really broad brushstroke, but these are all some of the things that are impinging on what happens in the classroom. So what do we know about what's going on in the classroom? Well, first looking at time for science, just sheer amount of time given to science instruction. In K-8, and there's been a couple of studies of this, one by the Center for Education Policy, and one I know of in the Bay Area, where they looked actually at time spent, particularly in K-5, on science, and that it really is getting pushed out of the curriculum because there's such a press through No Child Left Behind for accountability in math and science, in math and reading, and so you're not getting as much time on science. And incidentally, that's the same is true for social studies and the arts. They're also getting pushed out of the curriculum. Also, the push for coverage that I described in the standards, so you already have overall less time for science. Then you have standards that pack those topics in, so you have even less time overall to cover this huge number of topics. So you're really getting this scattershot, blow-through science when kids are learning in the classroom. And I did want to point out, at the high school level, one of the things we know, again, this equity theme, students in lower level science classes and schools, again, with high concentrations of minorities spends less time in science lab. So they're getting an even more impoverished experience with science. In terms of what actually is going on in the classroom, this probably is not surprising given sort of the convergence of elements that I've just described. It reflects a narrow definition of science, so typically it's what people have called final form science. It really concentrates on the facts, just the stuff that we know, and often it's not even a very sophisticated version of the facts. It's sort of terminologies and things like that. And this can lead students to think about science as sort of somehow this magical truth about the world handed down from on high, with like no insight at all that this is a human endeavor. People have gathered evidence, revised ideas over time. There's sort of no insight into the process of science in the sense of like, people just know this about the world, this is the truth. That's sort of emphasized again by teaching that focuses on recall rather than reasoning, and if you think about the problem of too little time and lots of coverage, it's going to reduce down to this kind of experience in the classroom. There's norms of the teacher in the textbook providing answers. So this is, again, related to this focus on the knowledge generated by science. You're either going to get it right, you're going to know what the scientist thinks, or you're going to get it wrong. Okay? And no room for sort of discussion and debate about that. Because I'm a little concerned about time, I won't go into details here, but the high school science labs sort of follow that same general trend with not a lot of time for discussion and sort of disconnected blow-through topics. So one of the really sad things about what's going on in classrooms is it completely flies in the face of everything we know about what we'd want to do to really have people learn things deeply and well, to really develop a flexible understanding that you could take and apply in your everyday lives, to really understand how science is conducted and have some insight into why scientists believe the things they do. We're doing exactly the things in classrooms that won't get kids there. So one of the things that we've done at the board, we convene expert groups to sort of study problems in science education. And out of that work, really looking at the research on learning and teaching, there's kind of developing a vision of what we'd like those classrooms to look like. What should science in classrooms look like to get kids to where we need them to be in terms of being to understand science and particularly to use that knowledge in their everyday lives? So it starts with reframing what we mean by science. So often, as I mentioned, in science classrooms, there's a real focus on just the end point, the knowledge in science. And I'm working from a definition here that comes from another National Academies publication called Science, Evolution, and Creationism. It's a fairly straightforward definition. But I wanted to use it as a touchstone because it puts in both the use of evidence to construct testable explanations and predictions, as well as that knowledge. And in classrooms, too often, it's just to focus on the knowledge and not the use of the evidence or even the gathering of the evidence and understanding that whole process. When we looking at studies from the history and philosophy in science, and even you're increasingly getting cognitive psychologists who actually go into science labs and look at how science is done, we're getting kind of a different vision of what science really entails. It's more than your controlled experiments in a lab. Science really involves building theories and models. It does involve collecting and analyzing data, but then you're interpreting that data and using it to inform how you're thinking about your models and your theories. You construct arguments. You put your interpretation of the data on the table and have a discussion about how well your interpretation might stack up against another one. It's really fundamentally a human endeavor done in communities, so it requires specialized ways of interacting and specialized tools and things like that. So what we're really looking at is a move away from very stereotypical depictions of science as sort of this lone endeavor where you have this scary smart person who toils by themselves. They're kind of maybe antisocial, a little nerdy, and they're really discovering the truth of the world. And instead, we're recognizing increasingly, particularly with our interconnected global society, that science is really this community. It's a scientific community composed of a lot of very diverse people who are working together to generate evidence, and then they discuss and debate that evidence. So it's really a very rich, exciting field, and not just the sort of sterile just the facts ma'am kind of approach we're getting in classrooms. So this is really what we want to engage kids in classrooms, the scientific community in a classroom. So based on this new and richer understanding of science, and also based on a growing literature of how kids learn science and what it means to really become proficient in science, a couple of our committees have put forward this idea of strands, so that instead of looking narrowly at science as only the facts, we think about science as this whole set of proficiencies. So strand one here, understanding scientific explanations, is really kind of the content of the strand, what we typically might think of content. It does include facts, but it's a broader set of things, like the concepts and the underlying powerful explanations in science. So, for example, you might have kids memorize the names of plants and the names of flowers and trees. You might have them understand the structures of them, but then you might have them do that in the context of mapping the environment of their schoolyard, coming to understand how different flowers with different kinds of structures live in different places in the schoolyard, and starting to develop an understanding of habitat. So you're getting a much more sophisticated understanding of these basic ideas in science. Strand 2, generating scientific evidence. This is, again, what you might typically think of the process is, but often that's reduced to the 5-step scientific method, or a narrow definition that it's always designed in a controlled experiment. And this is a broader sense of a lot of different ways of doing investigation that would range from what you might do as an experimental physicist, but would also include what you do as an evolutionary biologist or geologist, which is when you're a geologist, you don't go out and just do controlled experiments. You do a lot of field observations, historical reconstruction, things like that. Reflecting on scientific knowledge is really similar to what's typically called understanding the nature of science, and that is, as I described, the sense that science, ideas in science, understanding in science is revised as new data comes online. Now, but it's revised in a principled, methodical way. So it's not just, oh, we throw everything out. It's a test of the current ideas against the emerging evidence and the whole body of evidence. And so this is really understanding that process, but in addition here, it includes reflection on the status of the student's own knowledge. So it's how well am I understanding what's going on in this natural phenomena. And then 4, participating productively in science. This is often completely overlooked in classrooms, and this is the idea that science is carried out in a community, and you need to learn how to participate in that community and follow the norms in that community. That includes the language and the tools. It also includes sort of the norms for interaction. So one of them might be, what does it mean to argue in science, and what does it mean to win an argument in science? And in science, sometimes theoretically, that's supposed to be that you attack the evidence, not the person. I will say that doesn't always happen. But an argument is won in science on the merits of whether that interpretation really fits all of the evidence the best. That's really what's winning an argument. Now, the experience on the playground might be the biggest, loudest person wins. And so you really have to help kids understand this different mode of argumentation. So that's a reframing of science and a reframing of what it means to be proficient in science. We also need to reframe how we think about students' competence in science. So science has often been seen as sort of the elite subject, or one of the elite subjects, sort of like math, where only the smart kids can do it. And if you think about the way it's been presented in classrooms, typically when I painted sort of the current practice, it's no surprise that, it's going to take a lot to actually figure out something about science from the way it's being experienced by kids in classrooms. So we've got to sort of rethink how we're approaching things and assume that kids can do this. And in fact, we know that kids come to school with an incredibly rich knowledge of the natural world. And this is really all kids across the board. There's been international studies that have looked at this. People come with a lot of intuitive knowledge about the natural world. And now, some of it's implicit. So if you ask them a question about what they understood, they may not be able to tell you all of it. But when they operate in the world, they show that they understand. So instruction in K-12 needs to start with that foundation and build on it. Now, one of the things that have become popular in science education is to emphasize that a lot of that intuitive knowledge is wrong. There's an emphasis on misconceptions that kids come to school, and yeah, they know a lot, but it's so wrong. And what we need to stamp that out and put the scientific explanations in their heads. One of the things that that's doing is ignoring the fact that a lot of that intuitive knowledge works for them in the world. They're able to function, they're able to move and not bump into objects, they're able to understand things around them. That works for them. And so a more productive way to think about this for learning and teaching might be to look at the knowledge that kids bring and where is it correct enough, or where does it provide me entrees to lead that child to a scientific understanding, just to a better appreciation of the scientific explanations. So that's a slight reframe. You're going to acknowledge that some of these intuitive ideas, yeah, sure, they're wrong. But to approach them only head-on is not necessarily as productive. In addition, while all students can learn, it takes time and they need support to do it. And it's not hard to realize that it takes time if you think there are ideas in science really are hard. Some of them are hard. They're very counterintuitive. You think about atomic molecular theory, and then you think about all the things in the world and how different they are, water and the table and the book and, people. How could they all fundamentally be made of the same thing? That is incredibly counterintuitive. It took human beings hundreds of years to figure that out. A kid is not going to figure it out in a year. And they're not going to figure it out by just reading about it in a textbook. So they need time and they need support to understand some of these really sophisticated ideas. There's a lot of evidence, mostly from interventions in the classrooms, that kids are going to learn science, particularly this more complex understanding of what it means to learn science by doing science, but they need support to do it. So some people, when they think about having kids do inquiry, there's a tendency to turn them loose a little bit and have them just discover for themselves. The problem is kids don't understand how thought through scientific investigation is. And so you need to help them at every step of the way. And depending on how sophisticated the students are, they're going to need various kinds of support. So from framing a researchable question to figuring out what you're going to measure and how you're going to measure it, then how you're going to represent the data to answer the questions that you wanted to answer with that data, then figuring out how to interpret the data, figuring out how to figure out what interpretations are better. There's a whole set of steps, and kids need support to be able to do each of those. I want to point out it's particularly difficult to get to an understanding of the nature of science and these norms of participation. That's hard for kids, and they need support for it. And a lot of times in classrooms, the norms piece of it, sort of teaching kids how to act in a scientific community, is not supported. It's often sort of, well, kids are going to know how to do this. There's not necessarily a lot of intentional effort given there. And again, time for discussion and reflection. That's just a general rule in learning across the board, that kids need time to sit with these ideas. Oops. I'm going to blow through this one kind of fast. A similar trend for laboratory experiences in high school, and then these are sort of what we'd like to see with those instead. So more integration into what's actually happening. One of the ways that this has sometimes been done in some of the interventions is project-based or problem-based approaches. And actually, I have to give a nod to Brian Reiser, who was on one of our committees, who's at Northwestern here. This is his slide and work that he's done. But this is really one of the approaches that people have found can work. It gives you a way to hook students, to connect with things that they care about, or to find things that you can help them care about. So you can explain enough to them that they're going to be invested in really doing an investigation. So this is something that was done in the Chicago area, looking at a biological invasion in the Great Lakes region. And out of sort of this fundamental question, then emerged a bunch of different inquiry to answer. As one question got answered, additional questions would come up, and the kids formulate them with support from the teacher. So this is kind of the vision for the classroom. But then think about all these other elements of the system. How are you're clearly going to have to do something to those other elements if you're going to have this approach at the classroom level supported. And one of the clear ones that emerges first, I think, is this takes a very sophisticated teacher to be able to support this kind of learning and this kind of teaching, and not just a knowledge of science. So one of the fundamental things is professional development. Now, I'm not going to go into talking about pre-service training here, but it is a real issue. How do you do pre-service education that's going to support science education? But I'm not going to put that on the table here because there's a lot of issues related to higher ed that come in there. But ideally, what you want to do is try to have the whole system, all those elements of the system, aligned to all support this vision. So that means your professional development is going to be designed with that aligned system. We know from research on professional development, not just in science, but across other subject areas, that to be effective, it needs to be long-term and linked to what the teachers will do in the classroom. And sometimes that means linked directly to the curricula that they're using. So it needs to be immediately evident to them, how am I going to use this in my classroom, and sort of be more real-time. So summer institutes and things like that can be useful, but in order to really get true, lasting change in instruction, they need support across the year while they're trying this stuff. It's challenging to teach this way because it means kids are going to ask you questions you can't answer all the time. You need to address the knowledge of science, but also how students learn science, how to plan effective instruction, and how to use assessment. So when I talked about assessment before, and primarily I've been talking about large scale, but there's something that's typically called formative assessment that I really think of as part of instruction, which is what is the teacher doing in their classroom to figure out what do I need to do next instructionally? What do I know about where my kids are? And often there's not a lot of attention given to how to do that well, particularly in science. So other elements of the system, one of the fixes that have been suggested for standards and curricula as a way of getting away from this mild white inch deep and starting to be more focused is the notion of core ideas, or sort of focusing on a few key concepts. And the notion there is to take a good hard look at what already is in the standards and do some thinking about which of these are the most fundamental explanatory ideas in the core disciplines in science. So they need to be central to the discipline, but they also need to be teachable across multiple grades and have potential for sustained application across K-12. So the idea is you want to pick ideas that are going to give these kids kind of a lot of power to think about science. But you also want to pick them so they're not so sophisticated that you could only get to them when you're in 12th grade, because then you don't have time to investigate them. So over multiple grades is what you want to start to be thinking. And I will say the National Research Council and the Board on Science Education is at the very early stages of embarking on a revision to the standards that's intended to do this. So we're just starting a project on this. Assessments then need to be aligned to those kinds of standards. We also need to think about having a multiple assessment system, so don't feel like you have a stranglehold from No Child Left Behind to meet accountability, but think about a whole system where you might have different kinds of assessments, some of which are going to be for accountability and some of which are going to be more geared to giving you information about what's going on in your classroom. And so that every assessment has to be designed with a specific purpose. You're not going to be able to use one big large-scale test and find out everything you need to know about the learning going on. And we really want to try to push for assessments that are going to capture all 4 strands. Now, you might not be able to do that, but you at least need to be capturing more than just the facts, the narrow facts that are now often what these large-scale tests are testing. And one of the things that, the phrases that I often hear is that what gets tested gets taught. And so if that's true, and assessments are here to stay, they're not going to go away, accountability is not going to go away, that means make better assessments so that you're okay with what's getting tested being taught. So I want to end by taking a little walk through some of the research needs that are imperative for us sort of getting to this vision. So, and I would say this is research, but more like R&D, research and development. So in education, we can't wait 20 years where everybody works in their sort of toils in isolation from the school system. Kids can't wait 20 years to have better things happen in the classroom. So a lot of people had suggested that education research has to be more like engineering, and I'm saying more like R&D. So in standards and assessment, some of the needs are the learning progressions built around core ideas. So learning progressions is the notion that you can take research on how kids learn particular ideas and make hypotheses about how that learning will extend over multiple grades. You kind of build a hypothetical trajectory that includes thinking about what are the instructional things you need to do to get them to an understanding of that core idea. And the National Science Foundation has actually already funded some teams to be doing this work, the learning progressions work, and the work that the National Research Council that we're just starting is going to try to be framed around this learning progressions idea. Then you want to try implementation of standards that are built around core ideas and learning progressions, but study them as you implement it. So understand what's going on when you're trying to use this and use that to reflect on what you might do next. And then you need large-scale assessments that are in parallel to this new approach to standards and that include performance tasks. So you need to open up large-scale assessment to be able to capture some of these elements of science that are more about the reasoning, use of evidence, interpretation of evidence. And there is some promising work leading to doing that. So the revision of the National Assessment of Educational Progress for 2009 tried to push that envelope. And there's a lot of promise from computer-based assessments that can be done on a large scale, which include, for example, simulations of phenomena and things like that, which allow you to do a lot more flexible things in terms of assessing kids. In instruction, we need more classroom-based studies. So we know a lot about, there's actually a fair amount of work that's done more like laboratory work with kids, understanding science, but it is really different when you're working in a classroom setting, particularly when you're trying to push kids to work in groups and be more of a community. We don't know a lot about how to support diverse learners in science. For a lot of kids, science is like a foreign culture. It's just not congruent with the things that they do in their homes. And I mean, I would say a lot of kids, not just folks in groups we typically call, those who have some issues in school or are underrepresented in science. I mean, it's not easy, particularly when we're talking about science the way we're doing it. But there's particular challenges when people speak English as a second language and you're learning all these terms, when you have different modes of interaction, like the kind of questioning you do in science may not be fully accepted for some ethnic groups. So there's a lot of need for research on diversity. And then scaling up successful approaches. A lot of the insights about instruction that I've described come from what might be called hothouse projects. So they happen in one place and very close to the people who developed and implemented the initial trial, but we haven't really tried to put them in more places. And it's that scale up is a bear. That is where things fall apart, and we really need to understand a lot more about that. Professional development, obviously this is a linchpin, and again, pre-service is an issue too. At K-5 particularly, there's a real need to think this through Is it reasonable to have K-5 teachers teach all subjects? And if we're going to push for this kind of science, is it really something everybody's going to be able to do? Specialists is a model that's out there as a possibility. A lot of pros and cons to that. And then thinking through to what extent and how do professional development needs differ by grade level. So high school teachers teach standalone subjects, and they often are going to come with more of a grounding in the science, but they may have experienced courses in undergraduate in their science preparation that are the antithesis of what we actually want them to do. So just think back on your science courses in undergraduate. Did they look like the vision that I described? Probably not. So that's what the teachers are experiencing. And I just wanted to highlight again, I covered a lot of ground very quickly. I kind of pushed for coverage, which is, not great, but we have time for reflection and discussion, so that'll be okay. But what I haven't touched on is school organization and administration, which is a big piece of this, and relates to things like science specialists in K-5 and the kind of support that you'd give them. I haven't touched on higher education, although I've alluded to it, and I think we can see there's probably some issues there. And particularly, I haven't talked about informal environments for science learning, which are like museums and aquaria and parks and all the things that are available where they could work in better synergy with schools and be capitalized on more effectively, but really haven't been in the past to such a degree, or in pockets it's happened again. I just wanted to mention that a lot of the work that I've blown through is actually captured in a number of publications from the national academies, where we bring together groups to study issues and then write reports. And there's a flyer out on the front table which will give you discounts if you're interested now in these books. There's a little code on there, and it'll give you discounts if you're interested in reading more about any of the particular topics that I've put on the table. And it's actually more than I've got on this slide. There's actually a couple other books I got them to stick in there. So you might want to pick that up. And thank you.
Great. Thank you for a thought-provoking lecture. Now we'll turn to panel discussion. So let me introduce each of our panelists in turn. First, we have Professor Jeanne Sentry. She is the Director of Science Education and Research and Evaluation at the Center for Elementary Mathematics and Science Education at the University of Chicago. Then we'll have Mr. Michael Lach. He is the K-12 officer in the Office of Teaching and Learning at Chicago Public Schools. And then finally, we'll have Ms. Gudelia Lopez. She is the Senior Program Officer at the Chicago Community Trust. After that, we'll have about 15 to 20 minutes of Q&A. And then following the Q&A, Professor Jim Spillane will provide his summary comments. He is the Spencer T. and Ann W. Olin Professor in Learning and Organizational Change at the School of Education and Social Policy and a faculty fellow at the Institute for Policy Research at Northwestern University. So why don't we start with Professor Jeanne Sentry. Thank you.
When I was reviewing Heidi's notes prior to coming here, it took me back a little bit to my graduate school years, because when I was in graduate school, this was over 20 years ago, when I was in graduate school, I was doing a piece on the history of science education, and I was reading pieces from different eras, from the mid-1800s all the way through the present day. And as I was reading these different pieces, I was saying, gosh, I just read this. I just read this. Didn't I just read this? Who said this? I just read this. And I realized that, in fact, I wasn't going crazy, and I was paying attention to what I was reading. And in fact, all of these pieces over time were saying very many of the same things. And it inspired me to start a little personal project. And that little personal project is to collect one book from every year, as far back as I can go, that says what's wrong with science education and how to improve it. There aren't so many on science education, but I'm doing that collection. I'm having to generalize to education in general. And I have to say that I went back to some of those books in preparation of my remarks, because I just wanted to confirm that it really was as nutty as it appears to be, and it is as nutty. So I'll go back to a couple things that Heidi talked about. Heidi began by talking about the purpose of science, and this is a long-standing issue in science education, of course, going all the way back to when science first entered the curriculum in the mid-1800s. There was a conversation then about introducing science so that we can discipline our minds, and then other people wanted to introduce science for daily life. And I did some work in the Obama-Biden campaign in the transition, and when we were talking about how to communicate about the purpose of science, we kept talking about competitiveness as well, at the same time that we were talking about the importance of people being able to interact with their world and being participatory citizens and being healthy and making smart choices and all of the things that Heidi talked about. But of course, the competitive argument is very compelling, and often the other points of view get short shrift. But my overall point here is that this is a long-standing issue going back as far as science goes back in the curriculum. Another thing that Heidi talked about was this disjointedness, or not disjointedness, but sort of the need to align all of these different parts of the system. And this is also something, let's see, she talked about articulation of the program and what science is necessary and how to sequence it, and what criteria should we use to select content, what kind of instruction do we need. And I'm reading from a list here, but I'm not reading from Heidi's list. I'm reading from a list from the Yearbook of the National Society for the Study of Education that was published in 1960. So this is a book from my collection. It just confirms that we've been revisiting some of these issues over time, but for some reason we're not making a lot of progress. And the third thing that Heidi talked about was this vision for science. And this vision for science is also something that has been around for a very long time. This interest in moving away from focusing on only facts and knowledge. And this is where I drew this quote from, right? So John Dewey said in 1928 that knowledge, it's taught as a finished project. He wasn't talking about science specifically, but a finished product with little regard either to the ways in which it was originally built up or to changes that will surely occur in the future. To large extent, right, he goes on to say, the cultural product of societies that assume the future would be much like the past, and yet it is used as educational food in a society where change is the rule, not the exception. So basically, we're deciding to teach things in school that we know can't possibly be relevant as society changes. And John Dewey said this in 1928. So my point is that we have had a lack of vision. We've had a vision for this for many, many years. And it's not that we haven't understood what the problem is. My point is that we haven't been able to figure out how to enact our efforts so that they stick and so that they last. Oops. That's all that slide says, right? So how can we bring about changes that will last? So I gave this a little thought and asked myself, well, what is different about today? Because I'm optimistic about today. I had some real eye-opening experiences when I was working in the campaign and the transition. And I felt a little bit frightened and a little bit optimistic. So I'll tell you why I think today holds a lot of promise for us to get out of this rut that we're in. So one of the reasons, Heidi mentioned it, she said that science is often spoken about in the context of STEM, STEM education. And one of the differences between how science has been handled in the past and today is that, in fact, I think STEM is no longer just a convenient acronym, or at least it's becoming something that's different. People are starting to use STEM to mean something more, something holistic. And what I've noticed, there's no set definition of this, but what I've noticed, I think people are starting to use STEM as sort of a synonym for all of the good things we envision about science education. And I have a hypothesis about why. People are saying things like a STEM way of thinking or a STEM way of solving problems. I see this all the time. I think it's because people are realizing that in order to do the kind of science that Heidi was talking about, the kind that we really want ourselves to be able to do and our children to be able to do, you have to look across all of these disciplines. They can no longer be isolated. That's the way the world works. The world is not functioning in isolated disciplines. So that's my hypothesis about why we're moving towards STEM and one of the reasons why I'm optimistic. Another one is school, that school is sort of going away. I mean, we still have school, of course, but Heidi talked about the informal environment. She didn't really talk about it much, but she mentioned it. And the fact is that the borders between formal and informal education are going away, which is a good thing because people who've worked in informal science education have perceived themselves, I think, as the people who do the good kind of science education, and school is like the bad kind because it's formal and it's that bad kind. Well, the fact is that because of the coming of technologies, kids, right, we know this, kids are learning 24/7. They have computers that they carry around in their pockets, and they access knowledge and learning all the time, except maybe when they walk into the classrooms. It's true, they get taken away. So that's another reason why I'm optimistic. So I see technology may have finally provided us with the means for moving forward. And maybe it's because finally it's in the hands of the kids. And we can no longer pretend or fail to do student-directed education because they're doing it themselves, and we need to give attention to that. So I'll mention, because I was thinking about, as I was doing this little walk through my past history, I came across another comment by John Dewey, which rang true for me, and then I'll just make two closing points. And it rang true because as I was preparing for this, my two children, who are 8 and 10, were in school at the University of Chicago Lab School. And I was thinking about the borders falling apart between, school and informal, and how we want kids to learn the way we experience the world, which is everything holistically. And I found this comment that John Dewey made in 1899, right after he founded the University of Chicago Lab School. And he was talking about the goals for the school. And he said that they wanted to have education that would have a closer relationship to the home and neighborhood life, so that the things that the students learned in their classrooms weren't isolated lessons. And I thought to myself that it's 110 years later and they're still working on it, that it's not there. So how is that true? 110 years have gone by. Why is that? So here's the implications, the two takeaways here. One takeaway, there you go. What's different today, right? So one takeaway is that as researchers and reformers and leaders of reform, we've done a very poor job of bringing very specific and clear language to the work that we've done. We don't know how to communicate with one another. We don't know how to communicate so that we can systematically accumulate what we're learning and share it with one another, collaborate with one another, be coherent. We need to place the same demands on ourselves as we have expectations of our children. We want our children to use technology. We want them to collaborate with people over the world. We want them to engage in complex problems seriously. We need to place those expectations on ourselves. The second takeaway, I realized that as a person who has been doing science education for over 20 years, I no longer call myself a science educator. I call myself a STEM educator for some of the reasons I already gave you. But I had an aha moment recently where I realized that all of the work I had been doing for 20 years had been trying to realize goals articulated 50 years ago. Well, we know even before, longer than 50 years ago, 100 years ago. But I'm just referring back to Sputnik and sort of that era forward. So I had been working to realize this kind of education articulated 50 years ago, and a lot of elements of that are still very relevant and still very important. But I had to ask myself, how come we aren't enacting goals that were articulated for kids today? And why is that? So even as we still are enacting these goals articulated in this vision that we've been talking about for a long time, even as we retain those and implement them with our reforms, we have to look 50 years forward because we have to anticipate what is yet to come. John Dewey said it. The only certainty in our society is that it is bound to change. And we have to recognize that the things that we're trying to realize in classrooms today are not going to be the things we want to have happen in 20 years or 30 years. And even though we can't know what the future brings, we can do our best to anticipate it. And more importantly, As we're working to enact the reforms we identify today, we can enact systems for systematic learning so that we can continuously adapt, continuously improve, and continuously learn, so that we're not finding ourselves, or the people who are standing in our shoes 50 years from now, saying, well, we need to align the system. We need to figure out what standards. They'll have something to work with, and we would have made some progress from here to there.
Nice to be here. Thank you for including me, and it's always fun to talk to my colleagues. I learn a ton from you all every time I see you, so I really do appreciate it. What I thought I'd do is give you a little bit of a history of what we've done in science education and mathematics education in the Chicago Public Schools, looking back maybe about the past 5 years or so. I think you'll see, at least I'd hope you'd see, we tried to take everything that Heidi was telling us, that research said, and tried to figure out how to make that work in the third largest school district in the country. The Chicago Public Schools, as you all know, we have a very complicated system. For the past 5 or so years or so, we've focused on three goals, sort of three actually key strategies we've used to really drive our work forward. At the top was this idea that instructional excellence is most important. It's really that to really make a difference, you have to focus on kids and content and teachers and the almost magical interaction between them. And that's what's going to do the most good for kids. We also know that talent attraction and development is really important. You have to have great people, and you have to give kids as many opportunities as possible to learn and to develop. A few years back, we sort of said, there's a few other things we have to do here. We just need to support that with a really robust mechanism to manage our performance. These are big, complicated systems, and so we need to have metrics and systems to really track what we're doing and ensure we're getting the results we intend to. And we also had to deal with the issue of resource alignment, making sure we were putting our energy and our resources and our time and our money exactly where it's needed. So I'm not going to focus on most of these. I'm really going to concentrate on this instructional excellence piece. And over the past 5 years, we did come up with a sort of a system that, and we didn't plan this. It actually looks quite similar to Heidi's. Her slide is always so much more colorful. Her slide with all those different overlapping circles that came through. So our strategy around instructional excellence essentially had 5 components, and these 5 components had to all come together. This idea that you can't do one without the other was really, really important. So we would begin with this idea that high-quality curriculum materials is really, really important. You have to have pretty clear sets of goals and sets of tools that enable student learning and ideally would also enable teacher learning as well. Timely assessment data was really, really key, both for teachers and for program leaders, so you could decide what was working, you could make the mid-course adjustments that were needed. The in-school supports were also essential, and this is things like coaching, science specialists, team building, protocols, work to sort of make sure things really work in schools as well as they need to. It's probably not as much of that would really fit into the school organization and administration bucket that Heidi mentioned, and I'm sure Jim is going to take us to task for in a few minutes. One of the things we've learned in this process. And lastly, we had to have teachers who knew how to work with all this stuff. And this included not only teachers who knew their mathematics and science, but also who knew how to use their instructional materials, who knew how to make sense of the assessments, who knew how to work with coaches and their teammates at their school. And we surrounded this all with a pretty robust research and evaluation work so we could get feedback and data around all of this to make sure we're doing the right thing. We don't work in we don't do this by ourselves. I wanted to make sure I highlighted that there's many, many people in the Chicago area that we've been able to sort of pull together to move in the same direction. And if you don't see your little logo there, it only means I wasn't sophisticated enough on the website to pull it in. Many of you have been much more helpful than it's indicated here. But this has really been a partnership effort, using our university friends and our museum friends and our community friends to really help move things in the same direction, and that's been really, really powerful. Execution is always tough. We've been at this for a few years. We're slowly beginning to start to see data that seems pretty good. We've scaled up. This is mathematics on the left-hand side in the pink, and at the elementary level, and high school math and science at the green on the right-hand side. We've scaled up from very small beginnings to about 3/4 of our elementary schools and about half of our high schools, again, over time. It would have been tough to go much faster. We're sort of at the limits of our capacity. And we're seeing pretty decent results. Our evaluation shows this is about an effect size of about 1/3 of a standard deviation. My social scientist friends tell me that that's not too bad. And it's probably not good enough for the kids who are there and really deserve a better chance than they're getting, but we still feel that this is enough evidence to show we're moving in the right direction. So you can see almost twice as the rate of progress is almost twice as high for schools that sort of follow this full strategy here. And similar results at the high school, maybe not quite as dramatic gains, but starting to move in the same direction. We've tried to put in place, with a lot of your help, the research that we receive from our friends at the national academies and the comments we receive from people like you. And it's really important to be part of this conversation so we can keep learning and do even more to serve the kids in the city of Chicago. So thank you.
Good evening. My name is Gudelia Lopez from the Chicago Community Trust, and I'll talk a little bit about how we at the Chicago Community Trust have been able to support the school district, primarily in Chicago, but now looking to other school districts and improving teaching and learning, and I'll focus some of my comments on science. So first of all, just a little bit about our foundation. We are the region's community foundation. It was begun in 1950 with a gift of initially $200,000 from the Harris family. It has grown in assets to about $1.3 billion. It's shifting right now. We provide support in 5 program areas: arts and culture, basic human needs, community development, education, and health. And annually, these program areas provide about $30 million in support. So when I started the trust about 2 years ago, one of the first things that I was charged to do is to work with my colleague who is in the room, Peggy Miller, to look at the prior 5 years of education grant making. And we wrote a report that we had at the entrance about what we had done, what we had learned. And one of the things that we did at the beginning of the report is put some assertions about what we believe. So here are those assertions. We believe that all children are capable of learning much more than what we currently expect of them. We know, as Heidi said, they are born with, as being very inquisitive. They always ask questions. And somehow in education, as she mentioned, we tamp down on some of that inquisitiveness, and we have to do much better. We also know that schools must be organized to support teaching and learning at high levels and for continuous improvement. So schools need to be organized in this manner, both for the students, so they can develop the skills and knowledge they need to be continuous learners, but they must also be organized in a way that allows teachers to be continuous learners. And very importantly, we need skilled and knowledgeable educators. These individuals are essential for education to improve for our kids. And here's our challenge. How do we do this? And what we've decided is we need to support efforts that achieve large-scale strategic change. We know there are a number of different programs that can reach 10, 20, 30 students. However, we cannot support all of them, and we need to really get to the crux of the matter. What is happening in the classroom? What do we need to do to improve teaching and learning in science as well as the other fields? in the classroom time that we have with kids, with the teachers that we have in those classrooms. As Mike said, the district, any school district, any school can't do this alone. So we need to partner, and that has been one of our main goals and drivers. We need to partner with a lot of different institutions, a lot of different individuals, and many of you are here in the room who we've partnered with in the past and currently partner with. Also, we know that change takes time, and so we have to provide, as a foundation, supports that are going to give schools and districts enough time to see some of the change happen. As Mike mentioned, the school district is beginning to see some of those improvements in student achievement, but it's taken a long time for that to happen. Here are some of the critical elements that we see that need to work together in order for teaching and learning to improve. We need to have, as has been mentioned previously, strong curricular frameworks in all subject matters. And this is going to change and look different depending on the subject matter. For mathematics, it will look different in science. For literacy, it will look different in those two areas. We also know that we need to make sure that teachers have strong capacities to teach in these subject matters. And this means both knowledge and skills in teaching the subject matters. And in this arena, what we've been able to do is to provide support for graduate coursework for teachers at different institutions, as well as to provide support for those teachers in their classrooms. I think it was Mike and maybe also Heidi who mentioned that knowledge is not enough. And this is the case for students as well as for teachers. Simply knowing science is not going to change the way they teach science. They also have to have some skill in knowing how to teach students to develop their science education themselves. And third, one of the things that wasn't mentioned earlier a lot, but was alluded to, is this school structures. Schools need to be organized in a way, as I said earlier, that's going to help teachers learn over time, that's going to give them the support that they need. A principal needs to know what strong instruction in science looks like. They need to be able to provide that support for teachers to take the time to teach science and not only focus on literacy and math. Here's a project that we've been supporting now into its 4th year. This is the Cluster 4 Middle Grades Project. And this project, the aim of it was to strengthen teaching and learning in science and mathematics instruction in grades 6 to 8, and also to develop models for middle grades instruction for the district. So we've provided support so that teachers can take coursework at UIC in mathematics, at Loyola in science. Also, those two institutions have provided coaches to this project, and they are in the classroom with teachers implementing the curricula that the district has endorsed. The teachers, of course, have to take the professional development that the district has developed around these curricula. This project also provides support for teachers to take coursework that the district, along with a set of universities, developed for 8th grade algebra, to be eligible to teach 8th grade algebra in the district. So here's how we've been supporting science education. As I mentioned, we've been providing the coursework towards endorsements in math and science in this middle grades project, also for master's degree in content areas. We've also been supporting the university's capacity to work with schools and for the schools themselves to build capacities to be continuous learners. And one of the things that we've been doing just in the recent couple of years is providing supports to universities to improve elementary teacher pre-service preparation programs. So actually we just provided some support to the University of Illinois at Chicago and 3 other institutions, Northwestern University, Loyola University, and National Louis University, and they won a teacher quality partnership grant. And one of their goals is the goal for that particular project is to change their pre-service program in their institutions. And one of the things that they're going to do is to look across not only the School of Education, but also the arts and sciences to strengthen content knowledge across the board, including science. And here are some of the current partners that we work with. There are a number of other partners that are not included on here. We try, in any of the projects that we support, there is a very specific criteria. One of them being that it has to partner with institutions that have that, whatever expertise is a part of that project. Thanks.
Great. Thank you for some great panel discussions. Now we'll open it up for questions. We have microphones on the sides. If you have a question, if you could head over there, and I will just point at you, and you can take it away and ask your question. If you fancy yourself with a very strong voice, you can also stand up in the middle and shout your question, and hopefully we'll hear it. But microphones would be best. Yeah.
Thanks. People accuse me of being a loudmouth sometimes, so can you all hear me down there? Thanks. I'd like to ask to work on what Jeanne, you were saying about what's different today than in Dewey's time, and the science technology and this movement towards STEM as really STEM and interdisciplinary move. Do the other panelists or Heidi, do you feel that there are differences now that there were in Dewey's time that really make it a sustainable difference?
Yeah, I think there's a microphone.
I mean, I think that's a tough question to answer, partly because I don't really know what the policy arena looked like when those discussions were happening, but I actually think it's promising that, in my opinion, some of the most pressing policy issues of our time are related to science and technical issues like climate change, some of the health-related issues. I mean, they are fundamentally scientific, and I think we're going to run up against the problem that we don't have a citizenry that's sufficiently educated. And I actually think, although I have a problem with the competitiveness rhetoric, I do think that kind of the shrinking world is going to put into sharp focus that we're really poor, really badly off in terms of how well our citizens understand and engage with science compared to a lot of the world. And I think those two things really do, at least sort of in terms of policy momentum, they're meaningful. Now, whether we understand enough about how to turn a ship as big as the American educational system, I don't know. And that's actually, I think, the synergies with the informal science world are actually very exciting. And there's a lot of interesting work there. And that opens it up to being a discussion about public literacy in science and broadening it out to be more than just K-12, and including adults in that conversation as well.
I'll mention just one other difference that I see. I know you didn't really ask me, but and that's and that's that I don't know what the cultural perspective was in Dewey's time, but what I see today that I haven't seen in my career over the last 25 years is courage. And by that I mean I see in the people that I interact with in the STEM area and the fields that comprise STEM more willingness to give up the familiar. And I don't know if that comes from fear. I'd like to think it comes from courage, because I think people have always had the will, but not necessarily enough will to give up the ways of functioning and the ways of working that are so familiar to us, that are very difficult to let go of. But over the last 2 years or so, I've seen a shift. I've seen people really concretely demonstrate more willingness to give up that familiar, to find solutions to a problem that I think people are starting to see as our shared problem.
Actually, a lot of the recommendation for getting away from a mile wide, inch deep comes from international comparisons of curricula. And some of the higher achieving countries tend to do a better sequencing and focus on fewer ideas in depth over multiple years. So that it actually comes from some of that call for doing that in our curriculum comes from that emphasis. And in fact, when we're embarking on this new project to begin to reframe the science standards around that, we're going to be looking at some studies that have been done on international benchmarking and looking at what is done in the classrooms. Part of what's difficult is many of those countries actually have very different political will for how national education, how education is handled nationally. And we really have a complicated system because you have 50 states and it's really seen as a local and regional issue. And so sort of pressing for the kind of coherence that we really need can be tricky to figure out how to do that. So there are very different political and policy situations in some of the other countries. But I will say in general, and I don't do international comparisons, I did at one point, but not anymore. But in general, my understanding is Europe, in fact, does a much better job in science education across the board. And I understand, for example, in climate change, there's been much more efforts to do sort of public literacy as well. So I've actually heard people debate about whether we would be helped by mounting more of a public literacy campaign, because then you'd have more parents demanding high quality science education if you were starting to have sort of a broader effort to increase science literacy across the population. Because right now you don't necessarily have a lot of parents asking for better science education.
If I can actually just follow up on that, you mentioned that a lot of the assessments today focus on knowledge rather than on the process of science. Do we have a sense that the international tests that are used to compare the U.S. to other countries focus on the things that we think are important? Do we really know that we're as behind as we are in some sense?
One of the tests that people point to a lot is the PISA, the acronym of which escapes me at the moment.
Science.
See, they don't know it either. It's the PISA. But they, if I recall this correctly, they look at 15-year-olds, and it's really an assessment of more like scientific literacy. So they're looking at more the application of science. They do math as well, more the application of that knowledge. So it's a slightly different kind of test. And that's now pointed to, as one of the indicators that we're not doing quite as well.
Let me just repeat the question for people who might not have heard. I think, and you can correct me if I'm wrong, the question was whether part of the reason we are where we are, we still haven't implemented what we've wanted in the past is because of the traditional or conservative parents who fear in some way that what critical thinking, what science education might lead their kids to question some of the things that they themselves have taught their kids.
I can give a piece of evidence that might help to clarify that. In my time leading science in the Chicago Public Schools the past 7 or 8 years, I've only received one letter or phone call from a parent about the subject of evolution, and it was to applaud our efforts to make sure evolution was included in the schools. Nobody else has ever talked about any controversial issues at board meetings or to me or my staff that I know of.
I have a question. Over here, this way.
Yes.
Yes, okay.
I'm with you.
One, and it's a point to something that Heidi, you brought up when you were talking about building a hypothetical trajectory, the progression. And so as you were talking about that, which I thought made a lot of sense, right? But where is your starting point to do that trajectory? Is it from the future working back, kind of like the Merlin principle, this is what we want to accomplish, and the way to do that, we're going to start here in K through 5 and then K through 12? Or does it stop at the college level? Or you're saying if we can get them to college, then this is what our plan should be? Or is it if we can get them through high school, this is how we're going to operate? So I was curious about how that progression was going to look like, what it was going to look like.
That's a great question. And so not a simple answer, but I'll try to do it a shorter answer. So researchers are tackling it in a lot of different ways. So some people are just looking at them across a few grades. But theoretically, the way they've sort of been laid out is what you'd want to start is, you'd want to start with what we know kids bring. So this sort of, there are a lot of common things that kids bring at the start of school. But then there really is a need for some discussion about what your endpoint should be. So it could be 8th grade, it could be 12th grade. But if you're talking about 12th grade, there's kind of an open question on the table, and in the new effort that we're starting, this will be a question that gets explored. Do you want at the end of 8th grade to have created this trajectory such that your endpoint is college readiness? Or do you want it to be work readiness? Or are those the same? Or do you want it to be whatever kids would need to know to participate as a citizen and sort of be what we think you should be as publicly literate? And we haven't really had much research on this or very much of a national conversation about what do we really want for the end of high school and what's the difference between those three. So it is sort of complex. What would you be aiming for? Right now the conversation is K-12, so it wouldn't go all the way to the end of undergrad. And I've had some discussions with people where they will say, well, if you're going for literacy, then what you probably want is at least define 8th grade as well, in case you're not going to get sort of more courses required at high school than you might typically have. And so it's a great question, and I don't think it's necessarily completely resolved. In the research world, people, have more latitude to sort of be deciding, well, I'm going to study this idea over just 4 years or something, and somebody else can worry about some of those more policy-related questions. But in my opinion, some of those decisions about endpoint aren't research questions. They're value questions. And so they're not going to be answered through research. They're going to be answered through some kind of careful conversation about what do we want for our kids. And I think that may be how the discussions start to play out. There is some work in math and language arts done by Achieve looking at, and they've done a whole initiative after this called the American Diploma Project. And they did some work asking about what does college readiness look like as opposed to work readiness. And their conclusion was that it's converging. So it would actually be the same endpoint anyway.
So I see somebody at the microphone, and I'm going to give precedence to people who are standing at the microphone. So if you want to have a question,
Thank you.
right now.
Heidi, that's a great lead into my question here. We've been talking about the state of science education from kindergarten through 12th grade. What about early grades? And I'd like to know your perspective. You talked a little bit about how students come to us, I'm an educator, of course, come to us with this natural curiosity. How do we actually build on that curiosity?
I can start. I think Jeanne might have some things to say. She's nodding, so I know she I think there's a lot that could be done in pre-K. And in fact, we've had some interest in kind of looking at that, and some elements of the work that we did in looking at K-8 explored what kids already know. There's clearly room to support more. From a personal perspective, I would want to put on the table that we need to think carefully about what kind of foundation we want to build for kids in general, and this problem of time. And thinking about, I could make an argument that in the pre-K years, I'd actually want to focus on literacy and math and get some things in place there and do some science-related work and have literacy that it's embedded in a content area, but that I don't necessarily have to go full tilt hardcore science that early. And in fact, some countries that do very well don't really engage deeply in science until kids are in 3rd grade. And I can see arguments for doing that. But I think kids have a lot of capacity in the early grades and a lot of interest. And so if you're going where your kids' interests are, then it might naturally end up being science. But I'm a little bit agnostic on whether it needs to be as sort of rigorous and carefully planned in those early years. And I know that there are probably lots of people who don't agree with me. But I think there's a tension about how much time you really have and the kind of foundation you want kids to enter school with.
Yeah. Front.
I have a question for Mike Lach. You mentioned the three strategies, instructional excellence, talent attraction, development, expanded options and opportunities. How successful would you say that you are at this point? You showed some figures, but I'm curious how you feel you're doing and how CPS is doing.
I would say there's an awful lot of kids in Chicago who still don't have a fair chance at a great education. So I think we still have an awful long way to go. There's been pretty good improvement over the past 5-6 years, but it's not enough improvement to be happy with.
Mm-hmm. Is there any hope to expand CMSI to 9th through 12th grade?
I think a lot of the ideas around the Chicago Math and Science Initiative are currently part of the instructional strategy at the high school level. So I think there's a lot of that work is already there. I don't want to predict the future, so I don't quite know where that's going to go. I think there will be a strong focus on trying to increase the educational attainment of Chicago kids in mathematics and science.
So what is the current requirement for graduation for Chicago Public Schools for science courses?
Right now, students are required to take 3 years of science.
Thank you.
Okay, a question from the back. Then I'll take the two gentlemen standing here, and I think we'll probably have to stop there, but go ahead.
As was alluded to, a lot of this is contingent on higher ed. And so I'm interested in hearing a little bit more about the Chicago Community Trust. You said you support higher ed. And what does that support look like? Is it merely financial? Are there other things? And from CPS, is that support adequate? Is that what support would be needed at the higher ed level to do the pre-service training?
I'm going to ask you to repeat the second part of that to make sure I understand it.
Well, just what does the support that you offer higher ed institutions in this realm look like? And then from the CPS perspective, is that support adequate?
Okay. So this is relatively new set of work that we're doing. And I will talk a little bit about to answer your question, where the state is at. The state of Illinois, ISB, IBHE, and others are looking at what do we have to do to change the certification process for teachers in order to ensure that they have a lot more content knowledge when they start teaching, especially in the elementary school. I mean, we know high school is a different story, but in the elementary school. As Heidi talked about where we're at in terms of the K-5 versus the 6th through 8th grades. In Chicago, it's probably worse than what she painted. In Chicago, teachers do not have endorsements in math, or science, literacy to teach in grades 6 through 8. There is no departmentalization as you would have in middle schools, and that's what the project that we've been able to fund for the past 3 years has provided the district a start on. And one of the things that happened out of that project is that the district changed their policy, which I'll let Mike explain if he wants, that would have or force teachers to have endorsements in those particular subject areas in order to teach in those grade levels. With the work that we're doing with there's 4 institutions, as I mentioned. With that work, we are providing financial support. We are also providing, in some ways, a common table for them to come and talk about this work. And we tend to be thought partners with any of the projects that we support. So we will attend their meetings. We will meet with them as they're developing this work. We are also in conversations with ISB and IBHE about the changes that they're seeing coming down the line, and we can provide some of that information directly and indirectly to those institutions. But I think in the long run, the institutions themselves see this as a critical thing that they have to do. And these 4 institutions in particular have really bought into this idea and are really going to begin to work on changing that pre-service programming that they offer And again, as I mentioned, it's not just within the School of Education. It cannot be just within the School of Education. In addition, we've also been funding the Chicago area deans of education, and this is about 22 institutions. And so the work that we've been funding there has been to understand the landscape across the Chicagoland area in terms of the universities and what programs they offer, how many teachers they produce, where the teachers are teaching, how long they stay there, and so forth. And these 4 institutions that won the TQP grant are going to, as they're learning and making these changes that they're going to be doing in their institutions, they're going to be sharing that with the larger group of 22 institutions.
Okay, why don't we take, why don't we maybe first take 2 questions over there. I feel bad for making them stand.
My name's Bob Johnson. I'm with the Structural Engineers Association of Illinois and also the American Society of Civil Engineers. You mentioned the acronym STEM, but I'm most likely you've read the reports that surfaced recently. The E in STEM is missing. A couple of questions. Do you wish to address the fact that within the context of K through 12, the engineering component is pretty much missing? But outside of the classroom, extracurricular activities, we're seeing more and more participation from the business community with regards to design competitions. You've probably heard of US First. There's the IIT Bridge competition. There's the National Engineers Week Future City competition. All these extracurricular activities that nobody addressed that are trying to provide additional science engineering education outside of the classroom and to some degree supported by the business community.
So I'll try to tackle that one. I think we feel engineering is really important for our kids. I probably have somebody once a week coming to me and asking to add something to part of our curriculum. I've never had somebody come to us and tell us to take something out. I think a couple of the takeaways from the National Academy's report and the National Academy of Engineering report on K-12 engineering is there are some sort of key engineering concepts, skills, ideas around designs, around constraints that are probably important. It's unclear how different they are from some of the science process skills that Heidi talked about. When I talk to university faculty members, I find it very difficult to understand how the different sort of preparation one would need for a freshman chemistry course versus a freshman chemical engineering course. Generally, when I push faculty members, they just want strong math, science, and language skills to do that. We have seen a lot of pretty good data that shows engineering tasks are very motivational for kids. They like to build things. They like the competitions, and we've really tried to grow a lot of those kinds of works in partnership with many people in this room and many people in the city.
And final question?
My name is Bob Rosenstein. I'm speaking perhaps now as a member of the executive committee of the new American Physical Society Midwest Prairie section. Last year I was at a meeting, Sigma Chi Sigma at Fermilab, and that experience I have relates directly to the question the gentleman raised from the floor. There was 600 students were having a presentation on the problems of intelligent design and what physicists had to do in the country to oppose it. Then we broke up in the panel sessions, and I can tell you there was a great deal of angst among the physicists there about the impact this intelligent design movement was making throughout the country. And so I think that the statement that Mr. Lach made was not necessarily typical of what happens throughout the school districts in the country. And so what can we do really to more or less deal with this intelligent design problem? That certainly came up last year, and now we have a problem of a movement underway of people to put global warming notions on trial. And I think we have to be very careful about this impact on how students will learn. And what are we going to do about those issues that are coming up in the society and may impede the type of critical understanding we want students to have about science issues.
Any takers?
I'll just respond. The National Academies and the National Academy of Sciences that the National Research Council is affiliated with do get involved in conversations about evolution. So they have gotten involved in written letters to state school boards and things like that. So there is an effort by the scientific community to push back on some of that momentum. And I also just wanted to quickly, in terms of the discussions about public understanding, there's actually an initiative out of the academies called the Science Entertainment Exchange, which they just started, which is designed to take on, for example, how Hollywood portrays science and scientific concepts. And it's really to provide a direct link to scientists as a source for people developing TV shows, movies, all kinds of sort of popular media kinds of things, and to really ratchet up how it's portrayed. And I think that's exactly the kind of thing that we need broadly to counter those kinds of movements that bubble up due to the lack of science literacy in the public.
Great. Thank you for all the questions. And now...
Excuse me. I've been up here a while. I'm sorry.
Sorry, no, I didn't...
Two very quick ones.
Well,
I teach in a Chicago public school, and there's a lot of talk about inch deep, mile wide. How do I combat the fact that we're a transformation school and we're being given an inch deep, mile wide curriculum that we are being told to teach? And two, if you can just tell me how high schools are partially graded on their freshman failure rate. So how do I balance the idea that I'm supposed to pass this percentage of my students and still keep up a certain level of rigor? That's it. The best for last.
So there's a couple. Let me see if I can rephrase the question. So one is the district's curriculum is an inch wide, mile deep. So what do I do with that? The second question was had to do with freshmen on track rates, and I don't think I quite got it, but it had to do a question about what am I supposed to do with there's pressure to not fail kids, but also pressure to pass kids because you want to keep your numbers so you don't have huge failure rates. Did I get that right? Well, it certainly doesn't do people a lot of good to pass kids who shouldn't pass. So you shouldn't do that. But I know that sort of creates a lot of pretty intractable issues about how do you as a school start to tackle a lot of kids who are coming to you who are behind and who may not have great attendance in places where you don't have a team of teachers who is committed to doing the same thing or who works very well together, so you can't really be strategic about how to use your data in those kinds of ways. It creates really tough problems around that. I think we do have pretty compelling data from our friends at the Consortium on Chicago School Research that shows that freshman on track number is really, really important. And making sure kids are on track really matters. But nobody, I think, would argue we want people to change grades or inflate grades or change pedagogies in order to create those kind of grades, create grades that would make some bureaucrat downtown happy. We want to do the right thing for kids to do that. To the first question, the curriculum that the district has adopted, we tapped into the smartest people we could find in science. We talked to all of our local university friends, and we're constantly revisiting that every year with teams of teachers. It's also, we don't really tell teachers, hey, here's a script, you have to follow this through day 1, day 10, day 50. We use this as a guide for you to enact this curriculum in a way that works best for your kids in your school, in your context. We'd like to think we've got something akin to, and a very elementary version, mind you, of the learning progressions that Heidi talked about built within there, and our academic partners, I think, would also attest to that. But it's there for a guide for you to do that. So I'd encourage you to talk to your team of teachers and figure out if you need to spend a little more time on something, then do that. If you need to spend a little less time on something, then do that. But I do it as a team, and I do it in consultation with all the supports that you have available.
Great, thank you. And now we're going to finish with some concluding remarks from Professor Jim Spillane. Thank you.
Good evening. It's great to be here. It's great to have such good company. It's never a good idea to hold people from their food or their beverage, so I'll try and be brief and stick to the 5 minutes. Let me start. I'm going to try and make 3 points. You always have to have 3 things, they tell me. So first of all, let me start with those immortal words of William Faulkner. The past is never dead. In fact, it's not even past. And if there's one lesson from this evening, it is that we need to go back to 1776, maybe 1775, to the founding of this country and to that first 25 years or so, because there were some decisions or some things fell out at that time that actually everything Heidi put up here can be taken back there. We have a federal government that is constitutionally challenged when it comes to education. It has no authority whatsoever. That authority lies entirely with the states. The states are impoverished when it comes to an infrastructure to support education. Some states do a much better job than others. But for the most part, they have not had, and they have relied on the federal government for funding to try and improve their infrastructure. It wasn't until with Title I in the 1960s that states began to expand their departments to have staff and stuff like that with federal money. So I think it is very important. I love Jeanne's view of the world, and I want to live in that view. But I want to, let's have a little bit of caution here that we see what's possible. It's an administratively weak state, and as Heidi pointed out, with lots of local jurisdictions who provide a big chunk of the funding and where a lot of the decisions are made. As a result, we have a governance for instruction in this country that is muddled and that is constantly being remade. If you have not read American Creation by the historian Joseph Ellis, I would pick it up and I would read it. It is an excellent and very readable account of what I'm talking about. Lots of people have written about this, but I think it's important. There is no federal stick for science education yet. I'm not arguing there should be one. But as Heidi pointed out, the ones for mathematics and language arts had unintended consequences with respect to science. And I think it's important to keep that in mind. We do not necessarily agree on what we should teach with respect to science. Chicago, we may not talk about evolution. Kansas is just an hour away. Keep that in mind. So this is very much an American problem. Our school system did not grow out of the nation state like the French or out of some colonial power like in the case of Ireland or India. It was a local invention. It bubbled up from below. The common school movement. And for the last couple of hundred years, we've been trying to work out who has authority over what. And the easy solution is everybody does something. The more the feds do, the more the states do. The more the states do, the more the local government gets involved. So this is a fundamental structural problem. Now, we could see challenge there. Heidi talked and others talked about national standards. Of course, we have two national standards, sets of national standards for science. But in part, it's not just a problem of the governance system. There's a vast extra system of textbook publishers, of testing agencies, of now providers for schools This system of, this extra system, some of it for-profit, some of it non-profit, has expanded tremendously in the last 20 years. If coherence is our goal, I'm not convinced that this expansion of the extra system is going to get us anywhere toward a more coherent science curriculum. Again, you can read a lot about this. Paul Hill has written about it, etc. I'm not against the involvement of the markets or the involvement of this extra system. It's very much the American way. But it brings up a whole set of issues around coherence. Now, governance is not the only problem. The second problem that I see, again a theme carried throughout the conversations tonight, is infrastructure. We do not have a well-developed infrastructure to support teaching and learning, period. But we certainly do not have it in the case of science education. If tomorrow morning I was doing a job at my house in Chicago in the North Side, an inspector would come out from the city, if I got a permit, to inspect, let's pretend I had some plumbing problems, to inspect the plumbing. That inspector would have a set of standards that he or she would be working with and make decisions based on those standards. Now, it's Chicago, there is corruption, and sometimes $20 can get you a long way. But that aside, my point is simple. There are standards, and for the most part, people agree that this is how the house should be plumbed, or this is the electrical system, this is the way you should wire the house, or this is how a balcony should be constructed, or a deck should be constructed. We do not have, in the case of teaching, standards like that. You can argue with me that teaching is not like being an electrician or being a plumber. Fair enough. Doctors have standards. We consider them a profession that we may want to aspire in education. I'm a former teacher. But in education, we do not have standards, or the standards that we have are so poorly developed that we can't go into a classroom and say, this is good science teaching. Now, standards are just part of an infrastructure. Heidi talked about assessments, tools of various sorts, a language for talking about science teaching. Imagine that. If we do not have a language, a common language for talking about science teaching, we cannot evaluate it, we cannot engage in efforts to develop it. My point is simple. Gudelia also spoke about, for example, the school organization. That's part of the infrastructure. But what seems to be happening, if you listen to Mike, he spent 5 years with his colleagues at CPS trying to build this infrastructure around high schools. We shouldn't have to invent this one school or one school district at a time. And this, in part, goes back to the governance issue. If I was in Washington, which I'm not, I would be thinking about the federal role in building an infrastructure that states and school districts can purchase and buy into. The international comparisons are important, but they're often very surface level. Infrastructure is one thing that a lot of these other countries have, and it's not just the governance arrangement. Thinking that if we moved everything to Washington we'll solve our problems, I think forgets some of the other things that go on in these systems, such as an infrastructure to support teaching and learning. Part of that infrastructure is a university system that prepares teachers to teach a national curriculum. Wow. You go to Northwestern, or you go to UIC, or you go to the University of Chicago, and you take classes to become certified as a teacher. I suspect that the classes might look quite different, despite state requirements. Finally, I do think we have to stress the inequity issue. It is again built into the system. Teachers are paid by local school districts. They're hired by a local school district. Some of the recent research coming out, in particular in the economics of education, It's really disturbing that our weakest teachers are often found in our poorest school districts, and within those school districts and within those schools, the weakest kids end up with the poorest kids, the kids who have traditionally been disenfranchised by the system, end up with the weakest teachers. It's a shame that here we are in New Century, one of the wealthiest countries in the world, one of the best graduate schools, universities in the world, and we have not addressed this problem. The empirical data is striking. You cannot dispute it. What do parents want? It's a great question. And I think it depends on where you are in this country. But one of the things we need to ask is, what do parents want? What does industry want? But also, let's remember, one function of education in a democracy is to prepare citizens to live in that democracy. So we should also ask, what does the state want? And I think we have to keep that in mind when we debate about evolution. Should we teach evolution? Should we teach intelligent design as an alternative? The values issue is alive and well, maybe not in Chicago, but I think in a lot of other places. I didn't want to be pessimistic, but I did want to, these challenges I think we have to face. If we keep ignoring them, they're not going to go away. Thank you.